Okay. So, oops. So first of all, thank you very much for the invitation. Even though I'm not here in person in Australia, I'm really happy to present my work on star cluster formation simulation. So first of all, I'm Yann. I'm a PhD student working at HiPAG in Grenoble with Estelle Moreau, and I work quite a lot with Daniel to implement new methods in Phantom in order to produce these star formation, star cluster formation simulations in the code. And basically, the aim of my project, how can I remove that? Sorry. Okay. Okay. So the goal of my project, PhD project, is to perform numerical simulations, fast and efficient numerical simulations of star-forming clusters. And from the beginning of the collapsing of a molecular cloud up to the moment where you don't have any gas and you have a newly born clusters full of stars. And the goal of this PhD is to test many initial conditions, include as many as dynamical processes that we can think of during this early evolution, to have a better statistical view of this early evolution and try to correctly sample the random variations that is due to the stochasticity of these particular dynamics here. But this is really complicated to compute and very expensive to compute if we want to have the full resolution to resolve every single stars in the cluster or in the molecular cloud. So I had to do a lot of numerical choices and compromises in order to have the best performance I can do and reach this quite large number for star forming simulation compared to the community. Okay, so in order to do that, I've developed a few methods in Phantom during this PhD. First of all, a new stellar dynamics model, state-of-the-art, to integrate correctly the motion of the stars in these dense environments, to control the close encounters, etc. But I will talk about that later. Also, few stellar feedback processes, and I actually now just one in the sense of H2 region expansions, but this should be upgraded soon, or I hope to. The next one is a new star formation prescription that allows me to perform individual star formation with a very low resolution compared to the state of the art in the community. And finally, more like a side quest that we've developed after the last Phantom workshop with Daniel and Timothy, a new self-gravity module that conserves the momentum, the linear momentum now in the code. But I will talk about that just a little later. So first of all, the stellar dynamics module begins with a new temporal integration for sync particles. So all the sub-step module in the code, which has been switched with a fourth order symplectic scheme instead of the leapfrog. And that's now the default option in Phantom. And the great advantage of this integrator, despite the very good precision compared to leapfrog, is that you don't have any backward substep during this integration, which means that it's pretty easy to use with velocity-dependent forces that we have in the current substep module. And most of it, the main point here is that this fourth order scheme is also the best precision we can get for the lowest ratio between force and force computation per step, basically. And that's very important in cluster dynamics because you have to do a lot of steps, so you don't want to accumulate a lot of errors in such dense environment. So that was essential. But anyway, when you have very strong interactions, very close encounters, or even tight binaries or multiple systems, you have to implement new methods that deals with this these errors to avoid the large accumulation and completely mess the evolution in long term. So you have to implement then regularization in order to follow correctly these encounters, but also introduce methods to have a better performances even with a good secular evolution. So here I'm showing you the evolution of a hierarchical triple, where I'm adjusting the velocity of the internal motion of the inner binary to betterly constrain the performance on the time integration, but still conserve the good secular evolution of this binary. As you can see here, I can quite well reproduce the secular oscillation due to Kozylidev oscillation. But these methods should be only applied on these subgroups or very close encounters. So in top of that, I had to implement a way to select these groups and apply this specific method only on these groups. So I had routines that selectively search around each stars the neighbors that could be potential member of groups, and construct a matrix of neighboring or adjacency matrix, and then do a connected components detection to build the subgroups inside my stellar clusters in order to really focus my specific methods on these subgroups. And it works pretty well. And with that, on my first paper, actually, we saw a performance improvement around 80 in some, where the constraint is the highest, but it could be really like way more above that if we introduce directly binaries with very tight semi-major axis. And that will be the case in my next simulations, actually. So that's very important. But with that, it works. The second module was on the stellar feedbacks, and for that, I choose to implement H2 regions. So H2 region is basically the results of the ionizing of the gas around the massive stars due to their ionizing radiation. The gas is heated at 10,000 Kelvin, and then you have a very strong pressure gradient that will push the gas and expel the gas outward the region of formation. And to sample that, you have a few algorithms, but the first one that I choose to use is the method developed by Philip Hopkins in 2012, where he chose to resolve the Strömgren radius, so the boundary of this volume, by distributing the ionizing photon of the massive stars, QH, to every particles that is close to these stars in a sequential manner. So basically, we are cycling over the nearest neighbors, compute the number of photons needed to fully ionize the particle, and then subtract this value to the total ionizing photon, and do it sequentially. You can then sample the whole region, and when you don't have enough photon to ionize the particle, then you reach the limit where the photon is depleted, basically. So it's fast and cheap. So that's why I'm using that. But the problem of this method is that it can only sample isotropic H2 region, because you don't have any information on the direction of the photons in this method. And also in a more numerical perspective, it is a bit ugly, because you have to search around each sources. And if the region is quite large, you will search for basically every particle in the simulation. And then you have to sort the particle to access sequentially these particles. And that's not very parallel friendly. So in order to avoid that, I'm thinking about a new method, but I didn't implement it yet, where I can select a specific solid angle for and divide this whole solid angle around the massive stars into fraction, and then apply this the same algorithm but only on a fraction that could be handled by an independent thread. This could resolve both the isotropy problem, but also the parallel problem. So I will definitely try that when I have the time to develop this kind of methods. The other one, which I recently merged into the main code, is the Jim-Dale inverse retracing method. In this case, you are targeting a particle and just compute the flux of ionizing photon that arrives at this particle, computing a specific integral here along the line of sight between the particle and the source. And if it is sufficiently high, then the particle is ionized. And with that, by applying that on each particle, you can resolve correctly the geometry of the HQ region. But so that's good to have a very good geometry, but that's quite slow because you have to cycle through each particle, and that results to be slow because to find these sample points along to compute the integrals, you have to cycle every neighbors and find a good one, and that's a bit inefficient. So maybe a solution could be a neighbor search along the ray and efficiently find these neighbors like that. But I didn't try that yet, and that's also a possibility for further development. And with that, I have my feedback module. Of course, I should have other feedbacks, but it is quite difficult to implement them and test it. So for now, I just have that. I will definitely try to have more in the future. The last, no, not the last. The following module is my star formation prescription. And basically, it starts as every star formation simulations. You have a dense clump of gas that could collapse. You test if it collapses, and if it collapses, you form a single particle that could accrete then materials to gather a mass. And in my case, I choose to check on very large clump of gas, something around 8,000 AU, that allows me to have a very low resolution and then speed up a bit the process, speed up the computation. But at this scale, this clump of gas during the star formation process can still subfragment, and then multiple stars can form inside one single particle. So I made the hypothesis that a random number of stars can form up to a certain maximum number that is a parameter of this prescription. And then the sink will accrete the material to form these stars. And again, this is also a parameter of this prescription, the fixed accretion time here, to AC. And after this time, a single particle is then removed from the simulation and replaced by the star that they potentially host. And the mass is randomly shared. The mass gathered by the sink is randomly shared by the stars, and the stars are placed inside the volume of the previous sink using a Plummer distribution. And with that, I can form individual stars without the requirements of very, very high number of particles that we should have in a standard way of doing star formation simulation. So that was the whole point, to save a lot of computation. And with that, I have the complete structure for doing my cluster simulation. But as I said before, we had a little side quest during this PhD. I mean, I have a little side quest with this PhD. And last year, just after the workshop, we tried to change a little thing in the self-gravity module. So a little bit of context. To compute this self-gravity, you have to approximate the computation, because the n squared complexity will completely blow the count of interactions that you need to compute. So you have to approximate, and in particle-based simulations and in Phantom, we are using a multiple expansion of the green function to approximate the potential, the gravitational potential, using the second equation here. I don't know why I don't have my cursor, but anyway, yeah, there it is. Can you see my cursor? Okay. And yeah, the goal here is to remove this integral here on the whole volume and replace it by an integral on the only a cell particle here, where we compute the mass moment of a cell inside our simulations, in order to just compute an interaction between one particle and one cell, which saves a number of interactions, a lot of interactions, because you have multiple particles inside the cell. And coupled with a specific tree structure, you can then have a lot of computation saved by using also an opening criterion that tells you if you can approximate the interaction or not. And with that, the complexity drops to n log n, which is way more suitable. Yeah. But that's the original method. In Phantom, we used a little different method, which is supposed to be much faster by doing this multiple expansion on 2 points to allow node-node interactions in this self-gravity solver. And that could save quite a lot of time. In the case of the old Phantom method, we are applying this expansion on leaf nodes, which could then give us a boost of 10 compared to the original MM, because we have 10 particles in each leaf nodes of the caddy tree. But these two methods does not conserve the linear momentum, because they do not guarantee that one interaction will be the same on the other side. So another method, which we call SFMM, but that's maybe a bad branding for this method. We have a problem with the referee of this paper about that. So if you have other suggestion, I will be happy to take it. But in this symmetric fast multiple method, as we call it, you assure that these interactions are symmetrical from one side to the other by doing a clever algorithm to compute the node-node interactions to assure this thing. And with that, you have momentum conservation. And also, you can also have a lower complexity proportional only to n. But that needs a recursive algorithm that is difficult to parallelize. And the whole point of this new paper is to propose a new algorithm that can remove these very ugly recursive algorithms that Walter Dennen proposed 25 years ago, with something embarrassingly parallel, where we are computing each interactions per leaf. So one thread can only be independent and compute every interaction it needs by computing every interaction between the branch in the branch, starting from the root to the specific leaf nodes. So that's good, because with that we have an efficient scheduling. It's also a plug-and-play solution, Phantom, but the problem is that we can also duplicate a lot of work, because many nodes are shared between leaf nodes. So we have to compute interactions multiple times, which is not very efficient. But recently, I've also implemented an interaction cache that allows us to store the interactions when we are computing once, and then just fetch the numbers in live when another leaf needs this interaction. And with that, we have pretty much the same performance as the old method, but with the momentum conserving. And as you might see that in the presentation of Daniel this morning, with that, we remove completely the problem of the drift here in polytrope binaries evolution, with a very good conservation of the linear momentum here, close to machine precision, but also a much more accurate, much more conserved angular momentum as well. But that's still a paper in review. I still have a lot of things to work on to be able to be published. But hopefully it will be quickly done maybe after the write of my thesis, which take me a lot of time now. I don't know if I have a lot of time for the following. How many time I have? Sorry.
5 minutes.
Okay. Well, it will be quick. Sorry. Maybe a bit slow. So I applied. So just following up on my work, on my PhD work, I applied all these methods on a typical prototype for my molecular clouds, an homogeneous sphere, classical with initial turbulent velocity fields, with a mass of 10 force masses, a radius of 10 parsec, but only 2 million particles, 2.5 million particles here, which allows me to do a lot of them. And actually, the first study that I've made in this framework was to try to characterize the mass distribution. And I did a lot of simulation testing the parameters of my star formation prescription with different values and try to identify the influences of these parameters on the mass distribution of the stars and try to fine-tune these parameters to canonical models. So that's ongoing work, and I will be very, very quick on that. The first thing I've noticed is that the feedback is a key element to predict the final distribution of stars. And if we have early feedback, basically we'll have a very sparse distribution of stars, like associations, very unbound. And if the feedback is happening lately in the simulation, then we'll have a very dense core that is still stable after the whole expulsion of the gas. So that's very interesting, and we didn't expect it that much at the beginning. On the mass distribution, we also see a lot of fluctuations. Here I'm showing you two distributions, the sync mass distribution at the moment where the stars are released, and the final star distribution in blue here. And what we can see is that we have a large spread over the slopes at high mass here, which are not really compatible with the canonical models. And basically, we don't have enough statistics on this study to confirm if we can strictly constrain these slopes or not. Maybe we have a hint that this slope is steeper with the IMF compared to the sync mass function, but that still needs to be discussed and confirmed with more statistics. What is sure is that the peak of this distribution is quite stable and can be controlled by the factor n max. When this value is higher, then the peak shift to the left, so lower masses, and that should be expected. But what we can see is that the quantitative value can be really well constrained by a simple analytical calculation, and then we can greatly fit this number to constrain this feature to the canonical models, something around 5 in that case. The accretion time doesn't really control that, and we still need more statistics. I will go a little faster, but this accretion time can control well the morphology of the cluster. And basically, when you have a very shorter accretion time, then you will form denser cluster and more substructure inside the distribution of stars. But also, you will gather more mass and convert more gas into stars, which is also a very good way of constraining if our star formation is accurate or not. And I will skip completely that because it's a little too much. And I will leave you with my takeaways So basically, Phantom is now capable of producing efficient cluster formation simulations with all these developments. It opens a large field of statistical studies on their properties, and this is really something that my team and will try to develop in Phantom and try to really dig into this new framework. We saw in this little first study that we can control the mass distribution, the peak of this distribution with Nmax, that the feedback is really important to define the morphology of the cluster, sparse or dense, and that the accretion time can influence this feedback by limiting the mass and control the morphology that is chosen at the end of the evolution. But again, I mean, this is a very narrow picture because we don't have enough processes of this, I mean, present in this early evolution. Typically, we lack of protostellar outflows that can regulate the star formation. We lack of primordial binaries that can spread the mass a bit more inside stars and then change completely the feedback landscape inside the region. Also supernovas that can modify as well the IMF at longer period, and also magnetic fields that is not activated yet, and probably Daniel will blame me with that, and I have no excuse for that. I should have tried, and I will definitely try in the next future. And with that, thank you for your attention, and I will leave you with my little film for the movie competition of one of my simulation of cluster formation. And yeah, thank you. Sorry if I've been late.
Yeah, we have time for just one question. Yep, go.
Hey Yann, thank you for the talk. I have a question which is worth like $1 million. Which is, do you have any idea to simulate the outflows from the stars at the moment?
Actually, that's a difficult question. The problem is that because I'm supposing that the stars has been formed after the accretion time in my prescription, I couldn't really introduce the outflows directly on the individual stars, which means that I should do a sort of prescription on my sync particles, which is a bit touchy, and I didn't really think about that yet. But yeah, I mean, if I wanted to implement outflows, I should probably do that on the sync particles. And the typical way of doing that in in star formation simulations is by just expelling a certain fraction of the accreted mass by the sync particle in a certain typical cone that is randomly picked or given by the spin direction of the sync particle, something like that.
Thanks.
Okay, let's move on. Let's thank Yann again.
Thank you.
Now the last talk of the day is by Janovic about radiation hydrodynamic of star disk collisions for quasi-periodic arrays. That there.